In the last video where we learned the chain rule, I made the comment that, in my opinion, the only way to really understand the chain rule is through repetition, doing a bunch of examples. So with that in mind, in this video, I want to do a bunch of examples. This first example looks kind of intimidating. We're taking the derivative of a huge mess. But I think if you pick it apart and use the information we already have, you'll be able to break this up into several smaller problems, each of which might feel a little bit more manageable. So the first step when you see a problem like this is recognizing that what we're taking the derivative of is a sum of three things. I have this term plus this term plus this term. Anytime I'm taking the derivative of a sum, I can rewrite that as a sum of those individual derivatives. And as long as I'm doing that, I might as well take advantage of the fact that I have this coefficient here, this 3, so I can pull that out in front of its respective derivative symbol. What I'm saying is we can rewrite this original question as the derivative of 10 plus the natural log of x squared plus 3 times the derivative of 10 plus the natural log of x plus the derivative of 5. We used to have one question, one d over dx symbol. Now we got 3 questions, 3 d over dx symbols. But the good news is any of the 3 are simpler than what the original question was. In fact, some of them are fairly obvious, right? Over here, we're taking the derivative of a constant. We immediately know that that's just going to be equal to 0. No work really even required over here. What about this middle term? Well, the 3 is out in front of the derivative symbol, so I don't really have to worry about that. I want the derivative of 10 plus the natural log of x. Well, that's just the derivative of 10 plus the derivative of natural log of x. The derivative of 10 is just equal to 0. The derivative of natural log of x is 1 over x. This middle term is just 3 times 0 plus 1 over x. In other words, 3 over x. This term's easy. This term, medium maybe, not especially hard. It's this first term that causes a little bit of trouble. If you look at this first term and you can see the chain rule, that's fantastic. If you can see the chain rule and recognize that the outer layer is the squaring and the inner layer is the 10 plus the natural log of x that's being squared, then you have a good shot at evaluating this derivative. Remember, for the chain rule, what we do is we first only focus on the red stuff. If you're taking the derivative of the red stuff, using the power rule, we bring the 2 down in front, and then we subtract 1 from this exponent, which makes it 1. And no, you don't have to write this 1 right here. I'm just writing it to really show my work and show where all the different pieces are going. The stuff in blue I leave completely alone, so I'm going to just write 10 plus the natural log of x inside these parentheses. But then I'm not done. I have to multiply that by the derivative of that stuff in blue, the derivative of 10 plus the natural log of x. This is just the stuff I have in red and blue above. I still have all the stuff in green, which I can simplify to be 3 times 1 over x. I don't have to write this 0 nor this 0. I only have one d over dx symbol left, so I'm almost done. I'll copy exactly what I have here, except maybe I won't write the exponent of 1 this time. And then taking care of the derivative in blue here, the derivative of 10 plus the natural log of x, as we've already seen up here, is the derivative of 10, aka 0, plus the derivative of natural log of x, which is 1 over x. Copying down this last term, I get the answer to my question is this expression right here. At this point, you're done with the calculus, but it's not a bad idea to see if you can clean this up a little bit, and you can. The way I think about it is this 0 plus 1 over x is just 1 over x. And 1 over x times all this stuff is the same as all this stuff divided by x. So I have 2 times 10 plus the natural log of x divided by x for this 1 over x, plus 3 divided by x for this 3 times 1 over x. As long as I have a common denominator, I might as well add these two fractions together. And as long as I'm adding fractions together, maybe I first distribute this 2 to get rid of the parentheses. That'll leave me with 20 plus another 3, in other words 23, plus 2 natural log of x, all divided by x. These expressions are all equal, but I'm partial to this last one, so I'm going to call that my final answer. The purpose of this example was, don't forget stuff you already know, right? Most of what we did here in green is just stuff you've learned weeks ago. The only new stuff is the red and blue stuff that's kind of sprinkled in here. However, sometimes trying to do new stuff inside the context of other things you've already done can be really challenging, which is what I'm trying to show in example A, and it'll turn out also example B. Example B, we're again taking the derivative of a sum, this time 10 plus the natural log of x squared plus 3x plus 5. I would like you to view this as the derivative of this 10 plus the derivative of the natural log of a bunch of stuff that I'm going to write in blue, x squared plus 3x plus 5. I think this is a good point to pause and see if you can finish the problem from here. Maybe by the end of the video, you won't need this color coordination and you'll be able to do the problem from the start. But at this point, I'd be thrilled if you could take it from here. The derivative of 10, because 10 is a constant, is just 0. To figure out the derivative of the natural log of x squared plus 3x plus 5, what I want to do is just focus on the stuff in red. The derivative of natural log of x is 1 over x. Therefore, the derivative of the natural log of all this stuff is 1 divided by all this stuff, x squared plus 3x plus 5. That's pretty tricky. This is the first time we've used the chain rule where the outer function was the natural log of x. Previously, the outer function was either an exponent, like x squared, or x to the 1/2 power, or x to the 8th power, or x cubed, or the outer function was sine of x, which ends up being not quite as confusing as natural log of x. There's something about natural log, I guess specifically that its derivative is 1 over x, that confuses students a lot. I wouldn't be at all surprised if you came up with a different expression than what I have written right here. But hopefully it's the kind of thing where after you see it done once or twice, you can sort of follow the logic and then recreate it on your own. It's worth pointing out that we're not done here, right? We still haven't taken the derivative of the blue stuff. We have to multiply that answer by the derivative of x squared plus 3x plus 5. The good news is that's a fairly simple derivative compared to some of the stuff we've been doing. The derivative of x squared plus 3x plus 5, that's just a polynomial. I bet at this point in the class you can just look at this and tell that it's 2x plus 3 plus 0. In other words, 2x plus 3. We're done with the d over dx stuff, therefore we're done with the calculus. If aesthetics are important to you, you might rewrite this as 2x plus 3 divided by x squared plus 3x plus 5. That's what I do anyways. All right, how about another example? The derivative of 2 times e to the 5x plus 1. First comment I want to make, this 2 is a coefficient. Don't forget the rules that you already know. We can take coefficients and pull them out in front of the derivative symbol. This is 2 times the derivative of e raised up to some power. That power is the 5x plus 1 power. E to the 5x plus 1 is an example of function composition. The outer function is e to the x, the inner function is 5x plus 1, and that's why I color-coded things the way that I did. Just like natural log is kind of a tricky one for students, e to the x is kind of a tricky one for students. It's hard to see the function composition here. But maybe with the color coordination, you'd be okay with me just taking the derivative of the stuff in red. Because the derivative of e to the x is just e to the x, the derivative of e to the 5x plus 1 power is going to be e to the 5x plus 1 power times the derivative of that 5x plus 1. This factor is the derivative of the red evaluated at the blue, and then I multiply that by the derivative of the blue. And yes, I know that this factor looks identical to what you see here, but that's a consequence of the fact that the derivative of e to the x is just e to the x. So if this is f of g of x, it's also going to be f prime of g of x, because f of x and f prime of x are the exact same thing. If you struggle with this, something that I often write on the board at this point in a calculus class, which I feel a little bit silly when I do, but I've been told that it helps some students, is that the derivative of e to the stuff, whatever that means, is equal to e to the stuff times the derivative of that stuff. This is true no matter what the stuff is, no matter what your exponent is here. This isn't really some new rule. This is really just the chain rule where e to the x is the outer function. But for whatever reason, that's one that students struggle with, so having something written like this can be kind of nice to fall back upon. You'll see this instance a lot in this class where we have e raised up to a power other than x. And when you're taking the derivative of that expression, this is how you do it. And it's worth pointing out that this even works if the stuff is just an x. Because it would say the derivative of e to the x is e to the x times the derivative of x, but the derivative of x is just 1. So it's e to the x times 1. It would be saying that the derivative of e to the x is just e to the x, a fact that you already know. Anyways, don't get lost in what we're doing here. We still have one more derivative left to take, the derivative of 5x plus 1. Hopefully at this point in the class, that's kind of trivial for you. We have 2 terms, so we take the derivative of each term individually. The derivative of 5x is just 5. The derivative of the constant 1 is just 0. So the derivative of this whole thing is 5. My answer is 2 times e to the 5x plus 1 times 5, which I'm going to rewrite as 10e to the 5x plus 1 power. 3 more examples. Maybe I can speed things up a little bit. This problem doesn't look like a chain rule problem. In fact, it looks like a quotient rule problem. I think we've done this problem before, or at least something really similar with the quotient rule. But what if you don't like the quotient rule? What if you don't want to use the quotient rule? Well, what you could do is you could rewrite this problem. You could think about this as the derivative of 5 times the natural log of x raised up to the negative 1 power. Because the natural log of x to the negative 1 power is 1 over the natural log of x, and 5 times 1 over the natural log of x is 5 over the natural log of x. The advantage of looking at things this way is now it's conducive to the chain rule and not the quotient rule. What you'd probably do first is recognize that the 5 is a coefficient, so I can pull that out in front of my derivative symbol. I guess I should make that red. And then stare at the natural log of x to the negative 1 power and see if you can figure out what the outer function is and what the inner function is. If you've gotten that far, you can probably finish the problem. I leave my 5 completely alone. I take the derivative of the stuff in red. I'm using the power rule here. I bring that negative 1 out in front, subtract 1 from my exponent to make it negative 2. Leave the stuff in blue completely alone, the natural log of x, but then I'm not done. I have to multiply that by the derivative of the natural log of x. It's worth pointing out that you probably could cut out a line here, right? I bet instead of writing derivative of natural log of x right here, you could write 1 over x, because you know that the derivative of natural log of x is 1 over x. What I'm saying is you could cut out this line completely and just write 5 times negative 1 times the natural log of x to the negative 2 power times 1 over x. And if you're really comfortable doing that, that's fine with me. I'm okay with you going straight from this line to this line. However, just like I said before, when we're cutting out lines in our work, you might not want to do that. Because, well, I think it would be perfectly acceptable for this problem. I think what you'll see are as the problems get more and more difficult, it's more and more necessary to show the different lines of work. It's so easy to get lost in your work if you do multiple steps in a given line that it might not be worth the tiny amount of time it saves you to skip this line in the first place. Whatever, I'll leave that up to you. Are we done? Well, with calculus we are. But I'm going to do a little bit of algebra because I want to expose you to as much algebra as possible. This 5 times this negative 1 gives me negative 5, and I'm going to divide that by this x and this natural log of x squared, because raising something to the negative 2 power is the same as 1 divided by raising that thing to the second power. Moving right along, what if we needed the derivative of e to the 5x squared minus 7x plus 1? Well, you got options. If you prefer, we can think about this as a special case of the chain rule, where the derivative of e to the stuff is just e to the stuff times the derivative of that stuff. But really, you don't even need that fact. Just make sure that you can see this outer layer and this inner layer. Then when you're taking your derivatives, you first take the derivative of the red stuff. The derivative of e to the x is just e to the x. So what I'm going to write down here will be identical to what I have above, e to the 5x squared minus 7x plus 1. But then I recognize that I'm not done. I still have to multiply that by the derivative of that 5x squared minus 7x plus 1. Great news about the derivative of 5x squared minus 7x plus 1. We're at the point in the class where you can probably just look at that and tell what the answer is. The derivative of 5x squared, because I'm pulling the 5 out in front and the derivative of x squared is 2x, is equal to 10x. The derivative of negative 7x is negative 7, and the derivative of 1, since 1 is a constant, is just 0, and since the derivative of sum is the sum of the derivatives, the derivative of this polynomial is 10x minus 7. Again, note the importance of the parentheses here. Without the parentheses, this stuff only hits the 10x, but we want to hit the 10x and the negative 7. This is the rare case where I don't really think that there's any simplification that you could do. I mean, if you wanted, you could distribute this through the parentheses to get rid of the parentheses, but I don't know if that's any simpler. I kind of prefer the answer just the way it's written. Last example in this video. The derivative of 1 divided by the square root of 8 plus 8 times the log base 8 of x. This is me trying to make these complicated, trying to confuse you. Don't let me succeed. What you probably want to do for this problem is first rewrite it into a form that's more conducive to the rules that you have. For a lot of students, that's the hardest part. Instead of thinking about this as 1 divided by the square root of a bunch of stuff, think about it as a bunch of stuff raised up to the negative 1/2 power. That stuff, the 8 plus 8 times the log base 8 of x, serves as my inner function, and the negative 1/2 exponent serves as my outer function. When I'm taking my derivatives, I focus on the stuff in red. We're again going to use the power rule to bring that negative 1/2 down in front. And then if we subtract 1 from the exponent, we get negative 3/2. We leave the inner function completely alone. So I'll just copy 8 plus 8 log base 8 of x inside the parentheses. But then again, we're not done. We have to multiply by the derivative of that inner function. If you could take the derivative of that inner function, you'd be done with this problem. Good news, you can. We got the derivative of a sum, that's just the sum of the derivatives. So take the derivative of the 8. 8's a constant, so it's just equal to 0. I don't even have to write that if I don't want. All that's left is the derivative of 8 times the log base 8 of x. I take this 8 and bring it out in front of the derivative symbol, since it's just a coefficient, and then multiply that by the derivative of the log base 8 of x. The derivative of the log base 8 of x is almost just 1 over x. You just have to remember to multiply the x by this natural log of 8 for this 8 down here. So quick recap, this 8 completely goes away. This 8, since it's a coefficient, lives right here. And this base of 8 creates this natural log of 8 that we multiply the x by. No more d over dx, no more calculus. If you want to simplify this, what you could do is recognize that negative 1/2 times 8 is negative 4. And that'll be the only thing up on the top of my fraction because the x times the natural log of 8 is already down on the bottom. And all this stuff is raised up to a negative exponent, which means put it down on the bottom of your fraction. I could write all this stuff raised up to the 3/2 power, but I'm going to instead write the square root of all this stuff, 8 plus 8 times the log base 8 of x, cubed. Because I prefer radical notation to exponent notation when the question is given in radical notation. I think this is what I would call my final answer. That's a lot of examples. Hopefully you leave this video feeling a little bit more comfortable with the chain rule than you did after the intro video. And I don't want to scare you or anything, but you haven't seen the hardest of the chain rule. What you have yet to see is the chain rule hidden inside other rules. So examples where we have chain rules inside product rules, or quotient rules inside chain rules, or even chain rules inside chain rules. What you'll see is there's one more level of difficulty with the chain rule, and that's what we'll do in the next video.